Okay, we are doing kind of a fun type of calculus problem. We are finding a volume by what's called cross-section and integration. And so we're supposed to imagine in this problem that we're going to be a tent designer, for REI or something like that. And we've got this simple little one-person pop-up tent, and we're going to try to be figuring out what the volume is using calculus. All right, so it's bounded by two parabolas. One is y equals positive 2 minus 1/8 x squared and minus parentheses 2 minus 1/8 x squared, and then the line x equals 2. So here's the line x equals 2, and this is a parabola that in the first case is going to be opening downward starting at 2. If we plug in -4, that gives us positive 2 minus 2, so it's going to be a parabola that goes like this, opening down, and then the mirror image going like this, opening upwards. So that's the footprint of the tent, but it has cross sections that are equilateral triangles, like many tents might. So let's try to picture that in 3 dimensions. It's going to be something like this, where we've got in 3D, we've got our x-axis like this, our y-axis like this, and then we've got a vertical axis going up this way. So if we go, oops, I think I didn't mark that. I said 4, but looks like I marked off 3. So we'll say 1, 2, 3, 4, like that. So there's 1, 2, 3, 4 going that way, 1, 2 coming to the front, and then it goes up by about 2 and back this way by about 2. So sketching that now 3D style is going to be something like this. There's our x equals 2 line. Then it's going to come through like this. It's not easy. You don't have to be able to sketch these things beautifully in 3D, but it doesn't hurt to be able to kind of picture it. Alright, so at each place, each one of these lines, there'll be an equilateral triangle. Looks like maybe my first sketch here isn't perfect, but it's going to be an equilateral triangle like this, and then it'll be an equilateral triangle like that. Equilateral triangle there. Again, there'd be one here at the widest width, and then here where maybe you could imagine a zipper going like that and the door. This is an equilateral cross section here. So that's the equilateral triangle. And so then the top ridge, maybe the bent tent pole, would go something like that. Okay? And then all this is the stretched tight flat surface of these equilateral triangles that describe this shape. Okay? So hopefully you can picture that. Well, we're going to use the basic principle that we've been doing with our volumes of rotation, just like when we've had something similar like this, again maybe in 3D, where we have some shape like this and it's being spun around, so we get something like that. There's our volume of revolution. And then the way we integrate it is we just sort of think about these disks that are sort of stacked together. And really what we're doing is we have a way of describing this area, and that's just coming from pi r squared. So when we're going to integrate from some beginning to some end, we have just a function that matches that area. And in this case it's circles, but in this case it's equilateral triangles. So if you recall your geometry of equilateral triangles, if all 3 of these sides are equal, then this is a right triangle, 30, 60, 90 right triangle, and if this is some amount like a, then this long leg, it's called, is going to be radical 3 times a. So here we're going to be at some point x out here. This is when x is equal to 2. Well, that distance that was a here, this will be just what our function value is. And then that height there is just going to be whatever this is times radical 3. So in this case, the area will be 1/2 the base, oops, 1/2 the base a times the height, which is a radical 3. So it's radical 3a squared. All right. Well, in problems like this, you almost always want to try to take advantage of the symmetry, which is that this tent, if I were to slice it down the middle like this, will give us 2 halves that are equal in volume. So if we think of half of our tent, this is the inside of the tent with some, I don't know, vertical mosquito netting or something like that. That would be the vertical dropping down like that. So our integral for the volume, the way we set it up, we're going to start here at -4. We're going to go up here to when x equals 2. And then I know that this cross-sectional area, well, I'm going to take half of it, so then I'll double it later when I'm done with that. That's going to be the area of this triangle, which I just said was 1/2 a times a radical 3. That's just for this smaller half. So that's going to be 1/2, and then radical 3 times, then it's the function for the parabola. So it's 2 minus 1/8 x squared. All right? So we have to square that then because it's a squared, but then we're just going to do this integral. So the 1/2 comes out and cancels, the radical 3 comes out, so it's just going to be radical 3, and then the integral of, from -4 to 2, this squared. So foiling this out, I get 4. When I multiply that in the rainbow part, I'm going to get 2 over 8, which is 1/4. 2 of those then would be 1/2, so it's minus 1/2 x squared, and then when I multiply these guys times themselves, I'll be plus 1/64 x to the 4th, and then dx. So that's my integral. So then it becomes kind of routine after this. You've got the radical 3 always out front, and then when I integrate that, it's going to be 4x, then minus 1/6 x to the 3rd, plus 1 over, what is that, 320 x to the 5th. And that's still evaluated from -4 to 2. All right? So, oops, I've been off the screen all that time, but I will show you now. All right? So there it is. And what will this be equal to? I'll see if I can sneak it in here. Radical 3 then times, when I plug in 2, that's going to give me 8. Minus, when I plug in 2, that's going to give me 8, so it'll be 8 over 6. And when I plug in 2, that's 32. Well, that's nice. 32 over 320 is plus 1/10. That works out well. Minus, and then I'm going to subtract. When I plug in -4 times +4, that's -16. Plug in -4 to the 3rd, that's -64, but that's a minus, so that's plus 64/6. And then when I plug in -4, that would be 2 to the 2nd. 4 is 2 to the 2nd raised to the 5th. That's 2 to the 10th. Happen to know that is minus then 1024. It pays to know your powers of 2. 320. Okay? So I'm going to evaluate that. So that would be then radical 3. And let's distribute in the negative, see how quickly we can clean this up. You can jump and grab a calculator if you want to beat me to this, but that is positive 16. 16 then times plus 8 is 24. This is a minus 4/3, or 1 1/3. Let's see, this 64, that's 10 2/3, and I am subtracting that now. I'm adding that when I distribute that, and then I will be adding that. So that is minus, what did I say, 10 2/3, minus 10 2/3. So these together make negative minus 12. And then this is 1/10. And then what is this? Let's see. 32 is 2 to the 5th, so that's 32 times 32 over 32 times 10. So those guys cancel, and I get 3 2/10, and that's a plus 3 2/10. Hope I've done this right, because that's coming out fairly simple. That's going to be 12, and then 13, 14, 15, and 3/10 times radical 3. So 15 3/10 radical 3. There you go. Standard, a lot of different problems will have different types of cross sections. You could have made a square tent, and this would have been a square, and then it would have not had the radical 3. It simply would have been this squared. So there are a lot of varieties of this type of problem. You can read through a few examples in our text. Thank you.